C of t x1.
Did you mean C adults?
Sorry, yes, you're right.
C underline.
Okay, so why we consider this? So first of all, you know, it says that there is an interesting grammar defined by just these two letters x0 and x1, and also our interest to this quadratic equation. Yeah, but this is just a remark, and maybe then. Maybe Laurent remembers this, so it was a paper actually by 4 authors. Right now, and Vladimir.
And that you know the very well.
So,
That you.
and it was about inversion of this series, formulas for inversion of this series when A and B do not commute are free variables. And one of the ways to solve this was actually go to a quadratic equation, and for this, and get also polynomials such that they are the number of their terms are Catalan numbers. So this is okay, but so this is just a remark. I don't need this for this talk. Now let me go to Hankel matrices. So I consider actually matrices of this type: Cm of x, Cm plus 1 of x, Cm plus n of x, Cm plus 1 of x, Cm plus x, Cm plus n plus 1 of x. So 1 and Cm plus n of x. Cm plus what was this? M plus, I believe, 2n here. Okay, now in this, I probably talked in this seminar when we talked about non-commutative matrices. You do not talk about determinants, you talk about what's called quasi-determinants. Let me just briefly remind what it is, but before I will write you the answer. But the answer for this is equal to x. The answer is x to n plus m, and here m is 0 and 1. And this is just the exact generalization of the standard properties. So let me just. So the cheapest way to explain this quasi-determinant, also not the most general one, is the following. So you take this matrix, and I need only this type of quasi-determinant, so I have this matrix. And then I take the inverse matrix. And I will take, and then this quasi-determinant is is actually V and inverse. That's what it is. But of course, if you want to compute, there are other ways to compute this. Maybe I will skip so these examples. But that's sort of the result. This, and so the proof is actually based, of course, on this proposition. So that's easy. Okay. Okay, well, I have to add that this expression in the commutative case, the ratio of the determinant of A to the determinant of the matrix, which you can just cross out the last row, the last column. Now, for a commutative version of this theorem, this determinant equals 1, this determinant equals 1, so the ratio is 1. And so if you apply epsilon to this guy, it's just 1. Now, so then I think we were interested in inversion of Hankel matrices. And this is because commutative inversions. Because of the inversions, actually inversion of this Catalan Hankel matrices. If you do this, then it's known that the entries are binomial coefficients. So that's what the motivation. On the other hand, how to invert matrices. So maybe the best way is just to take. So you take this Catalan matrix. First, you present this as a product of lower triangular and, say, upper triangular matrix. Okay, so let me just assume that here I have a matrix with 1 on the diagonals, and for the upper triangular matrix, I do not require this. So this is something here. Now, so now you can describe actually entries of these guys, but for this you need a little bit more noise. So I'm going to define truncated Catalan numbers. Now, in this case, I don't know if the classical analog exists. I don't know, but still I can define this. And so again, let me just, so that's fix this K and N. And let P K be just a set of all Catalan classes such that, so the Catalan path looks like this until you arrive to the last. And so so the last angle has coordinates n, y. And I will require that y must be less or equal than k. Then let me define C and K of X. And this is exactly like it was before, except that P belongs now to this special. Okay, I just, well, it's easy to confirm this. The position is, it's very easy that they are related by this. And so here, of course, I require that C and so L of X is 0 and L is greater than N. So it's like this. Okay, and now I can sort of also maybe I will give you an example of this. X, that's just X n. C and 1 of X is just X n plus some X p. Then the theorem says that Hm equal M to M, and I here 1. And now I have to describe entries for this matrix and for this matrix. Now the matrix for
What is HM?
sorry?
HM? HM.
I start with,
Oh,
with
yeah.
0 or 1.
Okay, yeah.
I start with 0 or 1. So that's just the way to.
Yeah.
As yes, and so that's this bar means that if I have actually so I have this and this is anti how to say, so anti-inversion. So when you read, you have to read all monomials from right to left. So just so it's xi, and then read from right to left. So that's this one. And this similar entry and this is for U of M. This is for L of M. This entry is C minus 2 plus M minus G x2. And so you need this, this product to get ones of the diagonals. Okay, but basically I'm more interested in the inverses to these matrices, which I will define right now. And so hopefully I will. Do you have 10 minutes?
Or 53. People like the back.
All right.
We have 5 minutes.
5 minutes, okay. I'll try to do this. So very briefly then, some non-commutative binomial coefficients. So let me take a set of indices. And then I define this monomial. So they're just alternating monomial. Then let me define f from so subsets then scale into this. So f is defined by and so after this, I can define actually non-commutative binomial coefficient like this. This is sum j from 1 and to k x of the index 0 to n minus k minus 1. I have to subtract from j. Okay, I have no time for examples, but I have time for recurrence relation. And so the recurrence relation looks like this. And k is just n minus 1, k minus 1. Plus n minus 1k x2 n minus k minus 2 minus 1 x2 n minus k minus 1 k to 1 n.
Non-commutative.
Yeah, that's non-commutative, whatever so it's called, yes. And now, so and then I will finish with the theorem. So I have HM LM to M, and And then I have then the ij entry for um is -1 if I plus j, I plus j minus 2 plus m to I minus 2 plus m x2j minus 2 plus m minus 1. And this is for inverse, sorry for the inverse, and here for the inverse, this is also minus 1 plus j. Here you have plus j minus 2 plus m to I minus 2 plus m. And, well, you have to take two degrees from Retakh. So I can stop here, so when you use this definition, you can write Q analog, specialized Q analog.
Thank you for beautiful talk. I'll be glad to answer questions in private.
Yeah, okay.